Okay, so these lectures are going to be an introduction to the diagrammatic approach to circle bimodules. I'm going to mention a little bit the classical approach, but I mainly want to talk about diagrammatics, as that's I think what's most interesting. And I'll start with some motivation, which comes from Lie theory. Okay, so because we're in Lie theory, we should probably have a Lie algebra. We're going to have, so let G be a semi-simple Lie algebra over the complex numbers. Now, inside G, we have a subalgebra B, which is the Borel subalgebra, which we heard Sam talk about yesterday. And inside that, we have H, the Cartan subalgebra. And if you're less used to working with Lie algebras, you can always think of G as the special case of traceless matrices, and then B is the subalgebra of sub-Lie algebra of upper triangular matrices, and H is the commutative subalgebra of diagonal traceless matrices. Okay. So this theory, all of these, its choice of Borel subalgebra and Cartan subalgebra introduce a lot of other machinery. So in particular, we get the following inclusion of sets. I'll explain what these mean in a sec. So phi, as in yesterday's talk, is just a root system. And phi plus is a set of positive roots. And sigma is a set of simple roots. And we also get some more sets which live inside H star, the dual of the Cartan algebra. We have a lattice lambda, and inside that, a sort of positive part, lambda plus. And lambda is going to be a lattice of dominant integral weights. Oh, excuse me. Lambda is just integral weights. And lambda plus is dominant integral weights. Right, okay. And also let UG be equal to the universal enveloping algebra of G. And again, if you haven't worked with Lie algebras much before, you can think of it as basically a gadget which lets you consider representations of a Lie algebra G as modules over an actual bona fide algebra. Okay. So what can we say about representations? Well, for each lambda inside our lattice, big lambda, we can construct a short exact sequence. So this element in the middle, I'll start with first. This is a bit, let's move this a bit. Right, so in the middle here, this module is called a Verma module. I should explain how it's defined. So it's defined via induction. The module C lambda here is just a name for the one-dimensional module, one-dimensional B module, which you get by inflating lambda, right? So lambda corresponds to a representation of H, and via an exact sequence that we saw yesterday in Sam's talk, we can turn this into a one-dimensional and thus simple representation of the Borel B. And then we can induce that upwards to a representation of all of G by tensoring, by this sort of induction. And in general, this is going to be an infinite dimensional module. And okay, it has a unique simple quotient, which is called L lambda. So this is a simple highest weight module. And it is finite dimensional, but only in some cases. In particular, only if lambda comes from this set, lambda positive, of dominant integral weights. And then n lambda is then defined to be the kernel of this projection. And in general, this is also going to be infinite dimensional. Right, and this sort of construction is quite general. In fact, you can build all of the simple highest weight modules in this manner. But as you can see, it's natural to consider infinite dimensional modules in this framework. And it's unclear if we should consider all infinite dimensional modules or if we should consider only some of them. And it turns out that if we consider all infinite dimensional modules, that's too many. We do need to consider some of them. But we do need to consider some of them. We need to consider Verma modules and these kernels in some way. So the first thing we need to do is decide which modules we're going to work with. So let's see if this works. Next page. Okay. So I'm going to label this as a definition / theorem, and I'll put definition in quotes for reasons which I will explain in a sec. Okay. So for lambda in lambda plus, in this kind of restricted set of dominant integral weights, we are going to write calligraphic O subscript lambda for the minimal subcategory of, well, okay, what are we going to consider? We're going to consider a subcategory of UG modules. But actually, we don't want to consider all UG modules. We want to consider UG modules which have, which are diagonalizable with respect to H. This is a very, I mean, this condition is very helpful and useful, and will mean that we can reason about these infinite dimensional modules in a similar manner to the way we talk about finite dimensional modules. So to denote this, I'm going to have a subscript H semi-simple, meaning that we're only considering modules which are diagonalizable with respect to the Cartan. Okay, minimal subcategory of this thing, which, well, it needs to contain some things. So first it must contain m lambda, the Verma module corresponding to this dominant integral weight lambda. And we need it to be closed under the operations of taking submodules and what else do we want to do? We want to be able to take quotients and extensions. Okay. Okay, so now I should say why I put definition in quotes here. This is not a standard definition. The standard definition of O lambda involves first defining a separate category O, which contains all Verma modules for any lambda, and then restricting to a block. But this is pretty complicated to write out, and it requires a lot of theory. This definition is equivalent, and I think it's better motivated, but it's harder to work with in practice. But if you want to see a real definition, you should look in a textbook like Humphrey's textbook on BGG category O. Okay. So that being said, let's consider an example. So we're going to take the simplest example that we can, which is G being the Lie algebra SL2. And this means that, this is a mistake I should have mentioned. Well, I can fix this now. The vial group, which is a really important thing, which again we saw in Sam's talk yesterday, is going to be W. And for SL2, the vial group is just going to be the symmetric group on two letters. So in other words, it's going to consist of the identity element and a simple reflection S. And I should explain what lambda and lambda plus are in this example, but that's actually pretty easy. Lambda plus is just the non-negative integers, and lambda is just the integers. And of course, the Cartan is one-dimensional, so it's going to be isomorphic to C. So this is H star, this is lambda, and this is dominant integral weights lambda plus. Okay, what else can we do? At this point, we should draw a picture of what the lattice looks like. See if I can do this. Okay, let's put this dot here, which is the origin 0. You can have 1, 2. Say we go up to weight n here. And then in the other direction, we have -1, -2. And for reasons which will be clear in a sec, this is going to be -n, -2. Okay, so lambda plus corresponds to the non-negative integers. So if I wanted to find O lambda, I just need to pick lambda, which is a non-negative integer. So we may as well pick n. And the indecomposable objects in ON, well, I can just list them. Well, I'll list them for you without proof. So first of all, you have L of n, the simple highest weight module corresponding to n. And you also have L of -n -2. And you also, and I should mention that this coincides with the Verma module, M of -n -2. And we also have the Verma module M of n, which I am also going to call P of n, which I'll explain in a second. We also have another module, P of minus n minus 2. And so L of n and L of minus n minus 2 are simple modules. They don't have any non-trivial submodules, but the other modules have some more interesting structure, which I should describe. So in particular, we have short exact sequences. Let's see. Sorry, that's a 0, not a calligraphico. So this simple module. So first we'll deal with M of n. And it turns out that this Verma module M of n is a simple extension between two simple modules. And then the next non-simple module I mentioned was P of minus n minus 2. So let's just write that first. And that projects to M of minus n minus 2. And it has a submodule isomorphic to M of n. Cool. Right, next board. Right, so I should explain, the first thing I'll explain is where this n and minus n minus 2 distinction comes from. Why not minus n? What's going on here? So to understand what's going on here, let's write rho, which is going to be a big sum over the positive roots. Well, it's the sum of the positive roots, but we actually take half the sum of the positive roots. This is a common thing which comes up in Lie theory. And for W, an element of W, the Weil group, and lambda, an element of the dual Cartan, we're going to define a new action. Now, the Weil group acts on the Cartan or the dual of the Cartan the usual way by reflections, but we're going to define a new action, which we call the dot action. And the way it works is W dot lambda is defined to be equal to W applied to lambda plus rho minus rho. So in other words, it's the same action, but you shift the origin to minus rho. And yeah, so if we do this in the previous example, we find that rho corresponds to the positive integer 1. And if you reflect n in the only reflection S that we have, you get minus n and then a minus 2 to correct for the fact that we're not reflecting in the origin anymore. Okay. So what can we say in general about what happened in the example? So in general, there are bijections, three bijections, which go from W, the Weil group, to, well, first, simple modules in O lambda. Sorry, that doesn't look like a lambda. And then next, Verma modules. In O lambda. And finally, projectives. O lambda. And I should explain how this bijection works. If you take a little element W and W, it's going to map this bijection, well, each of these bijections will map little w to, well, for simple modules, you map to the simple highest weight module with weight W dot lambda. For Vermas, same weight, but for the corresponding Verma module. And then for projectives, I haven't defined P, so but I'll what these modules are, but I'll say what they are in a sec. PW dot lambda, where P of W dot lambda is the projective cover of L, the simple module LW dot lambda inside this category O lambda. And at this point, I should mention that these modules are projective in the category O lambda. If you look in the larger category of UG modules, they are no longer projective. So I should, to be very precise, be calling them projective objects or projectives. Occasionally I might mess up and say projective modules, but just so that you're aware. Cool. So what can we say about? So yeah, the fact that these projective objects exist is another interesting fact about this category O lambda. Another interesting fact, which I'll go over right now, has to do with the structure of these objects. So for little w inside the file group W, there is a sequence of submodules starts with 0, P1, dot, 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 etc. to, I don't know, Pn, which is equal to this projective cover, PW dot lambda. So it's a sequence of submodules inside this projective cover, P of W dot lambda. And what can we say about the sequence? It has the property that the successive subquotients, Pi mod Pi minus 1, are isomorphic, are each isomorphic to a Verma module. And in particular, the last subquotient, Pn mod Pn minus 1, is isomorphic to the Verma with the same highest weight. So this explains, this explains where those modules P of n, P of minus n minus 2 came from in the example, and it also explains the second short exact sequence in that example. appear to be having some issues getting another page. Hold on. Ah, there it is. Oh, excuse me. Right. Okay. Right. So I've introduced a category O lambda, and I've said some stuff about the structure of projectives. Basically, implied that there are enough projectives. It's fairly clear that this is an abelian category by the way it's defined. And in fact, we've shown that there are finitely many projective objects and finitely many simple objects. So really, we should start talking about this category O lambda as if it were the category of modules over a finite dimensional algebra. And that's exactly what this next theorem is about.
I'm sorry, may I interrupt to ask a question?
Certainly.
Yeah, so you already mentioned that this category O lambda is an abelian category, but does it have the same abelian structure as the category of UG modules? Does it inherit the same abelian structure or two?
Yes, yes, it does. Yes, the abelian is inherited from the larger abelian structure of UG mod. Yeah, you only need to show that this property of being diagonalizable with respect to the Cartan is preserved under kernels and quotients, and that's not too difficult to show. Right. Okay. So, in any case, the next theorem should make the abelian structure of O lambda a little bit more clear, which is that O lambda, the category O lambda, is equivalent to the category A mod FD. So, in other words, finite dimensional modules for an algebra A. So for a finite dimensional algebra A, which is not dependent on lambda. So right. So the first part of the theorem, which says that it's equivalent to a category of finite dimensional modules over finite dimensional algebra. This is just basic facts about, well, this is standard facts about Morita equivalence and working with abelian categories. The part that is actually interesting and new is the fact that this algebra A doesn't depend on lambda. This is something interesting. So this fits right into the following problem, motivates the following problem, which is to find a presentation, ideally a nice presentation, for the algebra A. Oh no, it's frozen. Hold on one moment. There we go. So find a presentation for the algebra A. And well, okay, by general theory, we can actually describe, well, okay. First of all, there isn't a unique algebra A for which the above theorem works. A is only defined up to what's called Morita equivalence. But if we want to describe one candidate for what A could be, we could write it as the endomorphism algebra. I seem to be having problems. One moment. Hang on. Doesn't seem to be updating very well. Okay, there we go. Let's just keep it like this and hope that this works. So A is an endomorphism algebra inside this category O lambda of a big, huge direct sum over elements of the Weil group of the following projective covers. Yeah, so in other words, this isomorphism, sorry, this Morita equivalence means that in order to solve this problem, it's enough to really understand morphisms between the projective objects inside this category O lambda. So, right. So you can spend a lot of time trying to find, trying to describe all morphisms between these projective objects directly by working with constructions of these infinite dimensional modules directly, but that's actually really hard. And one way to, one idea which turns out to be incredibly useful for solving this problem is as follows. So instead of trying, one moment. Perhaps if I mirror the entire screen, this will work better. This isn't very good. So instead of trying to understand projective objects themselves, we're going to try looking at functors which act on projective functors which act on the category of projective objects. Okay, so this is sorry. Let's put this back into view. So we should describe some of these functors, which I'll do right now. So for each S inside big S, which is the set of simple reflections, in our Weil group W, there exists an exact self-adjoint functor so I'll write theta S. And this is a functor actually which works on all of O lambda to O lambda, which behaves on all of O lambda, but when you restrict it to projectives, it does some interesting things. In particular, if you restrict projectives, it preserves them. And moreover, if you have little w inside the Val group with, the length of ws being bigger than the length of w. So what does this mean? This means that if you write ws using just simple reflections, then you need more simple reflections than if you just write w with simple reflections. So if this is the case, then we have an exact sequence 0, which goes into of this verma, which goes into the theta s applied to this verma, which goes into the verma, but for ws dot lambda. Let's just move this. Cool. And I should finish. Oop. Moment. And to finish up the theorem, finally, if s times t times a bunch of other simple reflections all the way up to u is a reduced expression, for W inverse in terms of the simple reflections in S, then the projective object P of W dot lambda is a direct summand of, well, theta S applied to theta T, applied to a bunch of other functors, theta U, applied to M of lambda, where lambda is the your dominant integral weight, which indexes, which defines O lambda. So that's, I'll just put a stroke here to say that the proposition ends there. Okay. Thus, every natural transformation of the form, let's say, I don't know, theta S, theta T, theta U, to a similar functor, maybe a theta S prime, maybe theta T prime, theta U prime. Well, if you have a natural transformation of these sorts of functors, this is automatically going to induce it's going to automatically induce a morphism of modules in O lambda. Which modules? Well, the same take these functors and apply them to your Verma M of lambda. And inside, by the proposition, inside the domain and the codomain as a direct summand are the projective covers of certain simple modules. And it's in fact, we can say more. In fact, this is a morphism of projectives in general, because it turns out that M of lambda for lambda dominant integral is projective itself. And it turns out there we go. It turns out that all such morphisms arise in this way. So in particular, it's enough to understand these functors, theta s, theta t for different simple reflections and natural transformations between these functors in order to understand morphisms of projective objects, in order to come up with a presentation of the algebra A that we originally wanted. And probably have enough time to conclude with the following theorem. Large theorem due to Schroll, which is that the natural transformations between such functors this can be described entirely in terms of bimodules over the polynomial ring C adjoin polynomial ring of functions on H. And the bimodules that you get in this way are called, well, today they're called circle bimodules, but I'm going to call them classical circle bimodules, because later we're going to, because we're going to see in detail how to work with these sorts of things in a diagrammatic way without talking about bimodules at all. And actually, I should have time for one last statement before I finish. See if this works. Oop. Get a new page. And this is a theorem due to many people. So I'll put a few names down. Elias and Williamson, and also Chalanov and Elias, and in some ways also due to Lieblinski. Which is that the monoidal category of projective functors So functors which act on projective modules, including our functors theta s and all sort of compositions thereof. Or if you want, you can think of the monoidal category of classical Zergo bimodules. I should probably insert a classical there, just to be consistent. And this has, what can we say about this? This has a very explicit presentation, in particular an explicit diagrammatic presentation. Right. So next time, I will explain what this means. What does it mean for a category to have a diagrammatic presentation? And hopefully also start actually defining this diagrammatic category so that you can have an explicit look at working, so that you can actually see how to work with Zergo bimodules in a diagrammatic setting. And I think I can stop here. Thanks.